Assalamu alaikum. Myself Mohammad Ishtiaq. Today I am going to present our thesis presentation titled as Smart Grid Stability Prediction using different machine learning algorithms, supervised by Dr. Muhammad Asimullah Nabil sir. So our thesis presentation outline are as follows: introduction, objective, literature review, methodology, system models, dataset description, result, conclusion, future work, references. At first introduction, the global demand for electricity has visualized high growth with rapid growth in population and economy. It thus became necessary to efficiently distribute electricity to households and industries in order to reduce power loss. Smart grid has the potential to reduce such power losses during power distribution, and stability in smart grid is become so necessary. So we apply different machine learning and deep learning algorithm in smart grid stability prediction. There are two objectives in our thesis work. The first objective is to develop a program in Python language based on proposed different model that helps to predict SG stability. And the second objective is to achieve maximum accuracy of smart grid stability prediction from the comparison of different models. So, literature review. An author named S.K. Mamun Alajab, he proposed a model which achieved 99.07% proficiency in training and testing. Training and testing loss, our suggested model is 0.02 for GRU, RNN, and LSTM. It is 0.06, 0.08, and 0.06 respectively. In another work, an author named Ali Kashif Bashir, he used LSTM-based RNN for smart grid load prediction. The results showed LSTM RNN outperform other models, but evaluation across diverse dataset is needed. In another work, titled as a multidirectional LSTM model for predicting the stability of smart grid, the author created multidirectional LSTM, which known as MLSTM. This MLSTM outperformed the regular LSTM deep learning models which known as gated recurrent unit and RNN. So now methodology. At first, data collection. We collected our data from open source database Kaggle. Import libraries. We import libraries such as Pandas, NumPy, etc. in our machine learning program. Then import CSV. We import our dataset as CSV file into the machine learning program. Data visualization. We visualized our data. Mainly, we see the interconnected or how the data are correlated one another. That is for data visualization. Then data preprocessing. We preprocessed our data. We checked if they are in missing value or not. Then we convert our target feature, which is in string type, we convert it into numerical type. The target feature has two classes, stable and unstable. We convert stable class into 1 and unstable class into 0. Data classification. In this part, we classified our data into two parts, training and testing. 80% of data we converted into training dataset and 20% for testing dataset. Model selection. We choose 3 different models for our thesis work. Then model evaluation. We evaluate our model by different performance matrices. Output comparison. At last, we compared all the models by the performance matrix we got from the model evaluation part. So this is all for our methodology. System models. We have implemented 3 different models. They are naive Bayes, which is a classification model, k-nearest neighbor, which is also a classification model, and a deep learning model named as sequential model. So this is our dataset description. We, as I told earlier, that the dataset collected from the open source database Kaggle, it has 60,000 records. It contains from simulation of grid stability. There are 4 nodes, 3 consumer nodes and 1 supplier node. And in this dataset, there is no missing value as it is a simulation dataset. There are 12 predicting feature, 2 dependent variable, and 12 predictive feature. So now the features are tau1, which represents the reaction time of the producer. Tau2, tau3, tau4 represents the reaction time of the electricity consumer. Then P1 represents the nominal power produced by producer, and P2, P3, P4 nominal power consumed by consumer. And G1, G2, G4 are the gamma coefficient, and step, the maximum real part of the characteristics differential equation root. If it is positive, then stable, linearly unstable. If it is negative, then linearly stable. Then our target feature is step F, a categorical data. It has 2 categories, stable and unstable. So this is the data visualization. The image shows the data distribution where y-axis represents the frequency and x-axis represents the parameters that are varies accordingly as displayed. Here the blue line represents the unstable class and orange line represents the stable class. For tau and p parameters, we have seen that the distribution over all the overlap significantly. In the g parameters, it is seen that there are a minimal number of stable class where unstable parameters dominates the stable plot. On the step category, there the negative value shows that it is stable and the positive value shows that it is unstable.
Presenting myself, Raihan Rahman, ID ET193004. I am from Chittagong. In my thesis, my contribution is implementing the codes in Python language for our machine learning. I have generated the output of our model in Python language. Besides, I have also compiled the whole codes in the machine learning model for getting desired outputs. I have faced some challenge in this thesis work, like I have problems in understanding the Python codes because before this thesis it was not familiar to me. Now I am presenting my undergraduate thesis presentation slide. Let's start with result discussion. Confusion matrix and classification report of our model Naïve-Bayes. Confusion matrix is a table that represents the performance of a model. It helps us to visualize the output of an algorithm of how it performs by comparing actual value and predicted value. From the confusion matrix and classification report, we can see that in our 3,882 unstable data points, my model correctly predicted 3,805 data points. My model made incorrect predictions in 77 data points. We can also see that in our 2,118 stable data points, my model correctly predicted 2,071 data points as stable. My model incorrectly predicted 47 data points. ROC curve with AUC score of our model Naïve-Bayes. ROC means receiver operating characteristics and AUC means area under curve. ROC is the graphical representation of trade-off between true positive rate and false positive rate. From this AUC score, we can see that Naïve-Bayes got 98% AUC score. The more AUC score, the better the model performs. It represents the accuracy. This is confusion matrix and classification report of our model KNN. It is our second model. KNN means K nearest neighbor. From this, we can see that in our 3,882 unstable data points, my model correctly predicted 3,487 data points. My model incorrectly predicted 395 data points as stable, but it was actually unstable. We can also see that in 2,118 stable data points, my model correctly predicted 1,507 data points as stable, but it predicted 611 data as unstable. That was not correct. A confusion matrix has 4 parts: true positive, false positive, true negative, and false negative. This is ROC curve with AUC score of our model K nearest neighbor. We can see that AUC score is 80%, which is lesser than Naïve-Bayes. We have evaluated our sequential model by model accuracy and loss curve as a performance matrix. We used 10 epochs for accuracy and loss curve. At the last epoch, we can see that the training and validation accuracy is quite similar, which is 97%. That represents the model accuracy. At first, we have got higher model loss in first epoch, but the last epoch, the loss in model got decreased. This is classification report of our model sequential. It is our final model. In 3,882, unstable data points, my model sequential predicted 3696 data points correctly as an unstable. In 2118 stable data points, my model correctly predicted 2173 data points as stable. Model comparison. This is the precision recall and F1 score comparison of our three models for each class, stable class and unstable class. We can also see that Nightbase got higher precision, higher recall, and higher F1 score in each and every class. That influences the accuracy of the model. Comparison of model accuracy. We can see that Nightbase got 98% accuracy, K nearest neighbor got 80% accuracy, and sequential model got 97% accuracy. The first one, the best one is 98%, which is Nightbase. We have also made comparison with some existing paperwork of some models with our models. We can see that in existing model, RNN and RSTM got higher accuracy, which is 96% and 97% respectively. In our work, Nightbase got 98% accuracy. Nightbase also outperformed our else two models, K-nearest neighbor and sequential. Conclusion. In our work, we applied some machine learning and deep learning model. The proposed model will automatically predict smart grid stability fastly and correctly. We also showed the comparison with our model with some existing work. In future, we will try to use ensemble learning, such as bagging and boosting, to enhance the model's performance. If possible, we will generate the dataset from live grid system and make prediction that will make it more real-life problem. This is the reference we used in our thesis presentation. Thank you, everyone.